In section 3.4, we have 3 more theorems that we're going to discuss while we start putting everything together and using it to solve and graph these polynomial functions. We know how to find factors using synthetic division. How do we know where to start? So far, I've given you a number as a starting place, something to try with synthetic division. Our rational zero theorem helps us to find a starting place. Now, again, math speak, I'm not going to ask you to reproduce this theorem, but you do need to start understanding how to read it and how it applies to what we're doing. If I have a polynomial function, and you're noticing that it starts with some first term's coefficient, all the way down to my constant, and it has integer coefficients. So the coefficients in the polynomial are positive and negative whole numbers. Positive and negative whole numbers are integer coefficients. Where p over q, reduced to the lowest term, so simplified, is a rational zero of the function. P is a factor of the constant. This is the important bit here. P is a factor of the constant term, right there, constant. Q is a factor of the leading coefficient. There's my leading coefficient. So what does this mean? Well, the rational zero theorem gives us a list of possibilities. Things to try to start factoring our polynomial functions. A list of possibilities in the form of p over q. If a rational zero exists, if there is a rational zero, then it's going to be in that list of possibilities. Now, rational means it's going to be a fraction or a whole number, real number, fraction or whole number. The thing is, my list of possibilities, p over q, contains only rational values. Roots can also be irrational or imaginary. And if my roots are irrational or imaginary, they won't show up in my list. So the rational zero theorem helps us a lot. It gives us this list of possibilities. Just keep in mind that these are only rational numbers, not irrational, not imaginary. So our list of possibilities may not include all of the roots for the function. Okay, we're going to start with a really long list. Usually I won't give you a list that is this long, but this is a good place to start to see how it works. We're going to find the list of possibilities, the possible rational zeros for each function. Now, our list of possibilities are all of the values positive and negative. That's an important thing. Both positive and negative. So when we do our list of possibilities, we have to consider all of the positives, all of the negatives. P over q, where p is a factor of the constant, so right here. And q is a factor of the leading coefficient, so right here. So that represents q. Now, factors. P is going to include all the factors of 35. So let's think about our things we multiply together to get 35. Well, we've got 1 times 35. It's not even, not divisible by 3, by 4, by 5. There we go. 5 times 7 is 35, and we've met in the middle. So those are the only pairs. 1 times 35, 5 times 7. Those are my factors of 35. Now let's talk about q. Q is 6, so we need to think of factors of 6. Well, 1 times 6 is 6, 2 times 3 is 6, and we've met in the middle. So those are our only factors of 6. This means we've got 4 factors of p, 4 factors of 6. We've got to include all of those possibilities. Now, we're creating our list of possible rational zeros, p over q, and we want to include all the positives and negatives. So I'm going to start by saying plus or minus. P is my numerator, q is my denominator. Let's start with our denominator of 1 first. So p over q would be 1 over 1, 5 over 1, 7 over 1, 35 over 1. Do I really need to list 1 as the denominator? Those are just whole numbers, right? So that's the same thing as saying 1, 5, 7, 35. Then I'm going to move to my next denominator, denominator 2. So I'm going to go back to my list of possible values for p and put all of them over 2. So 1 half, 5 halves, 7 halves, 35 halves. None of those will simplify because my values for factors of p are odd. Now I'm going to go back to 3. That's my next denominator. 1/3, 5/3, 7/3, 35 thirds. None of those are divisible by 3 either, so those won't simplify. Now I'm going to go back to my next denominator, q, and put every value of p over that. 1/6, 5/6, 7/6, 35/6. Okay, it's a long list. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 positive values to try and 16 negative values to try. Most of those are fractions. I'll tell you right now, if I were trying to factor this, I would start with these whole numbers, right? Those are the easiest. I've got 4 positive values, 4 negative values that are whole numbers. Don't stress about the fractions. We're not going to be using many of the fraction rational zeros when we're working through this. Okay, let's go to the next one. This next one is a lot more achievable. We're going to find our list of possibilities, p over q. P comes from the constant. Q comes from the quotient or the coefficient on my leading term. My coefficient here is understood to be 1. So q is just 1, which means I don't have any fractions. All I have are those whole numbers, things over 1. We've already worked out our factors of 6 right there. So p is going to be 1, 2, 3, 6. Q is just 1. So when I structure my list of possibilities, p over q, 1 over 1, 2 over 1, 3 over 1, 6 over 1, those are the only ones I have. So I've got 4 positive choices and 4 negative choices, things that I can try to help me factor that cubed function. All right, so when our coefficient is 1, things are lovely. There's not a very long list. I don't have any fractions. What about this one was extreme? This one's going to be a nice kind of in the middle example. So let's work through it. We've got our value for q comes from the constant. 3 is prime, so that's just 1 and 3. Our value for p comes from the leading coefficient. 4 is 1 times 4 or 2 times 2. So I only have 3 factors of p. Remember we're doing, oh, I just did that backwards, didn't I? So glad I caught that. Guys, everyone is human. Everyone makes mistakes. When we're in class together, correct me when you notice me making a mistake. If we're in the video together and you can't correct me, send me an email later so that I can make a note of it for the next student who watches the video. Okay, so values of p come from my constant, values of q come from my leading coefficient. What goes in the numerator and what goes in the denominator absolutely matters. So list of possibilities, both positive and negative. P is 1 and 3. I'm going to put it over each of those. So over 1, that's my constants. When I put them over 2, and then when I put them over 4, so 1/4 and 3/4. So there's my list of possible rational zeros. I have 6 positive options and 6 negative options that I can try if I want to factor that 5th degree polynomial function. Okay, moving right along. That's my rational zero theorem, finding my list of possibilities, p over q. Remember, not every root of a polynomial function is rational. Some are irrational, some are imaginary. These values don't show up in my list of possibilities. What about these irrational and imaginary roots? Do we know anything about them? I'm so glad you asked. Yes, we do. Our conjugate pairs theorem applies to our irrational and imaginary roots. Think about your quadratic formula. We have negative b plus minus square root of b squared minus 4ac all over 2a. Well, if I have a value that's not 0 here, I'm going to have two roots, right? Because I have negative b plus whatever this is, and I have negative b minus whatever this is. This can be, if it's rational, the radical goes away. If the radical doesn't go away, it's irrational. If I have a negative value underneath that radical, they're imaginary. So if they are irrational or imaginary, I'm going to have two roots by necessity. That gets us to our conjugate pairs theorem. Our conjugate pairs theorem says that if our function, polynomial function, p of x equals 0, polynomial function, real coefficients, and the complex number a plus bi is a root, then its conjugate, a minus bi, is also a root. Well, what does this mean for us? It means that imaginary roots come in pairs, conjugate pairs. They're going to be the same except for that sign in the middle. And like I talked about right here, although the conjugate pairs theorem does not specifically mention it, irrational roots also come in conjugate pairs. All right. So let's do some factoring. Let's put this to work. We have a polynomial function. This is a third degree polynomial function. How many roots will I have to find through synthetic division? Well, I know that once I get it down to squared, I can factor. We found that out in the last unit, or not the last unit, the last section. Since this is third degree, I really only have to have one because I factor out that 1 degree and it's squared. So I need to find one root using synthetic division. Then the quotient that I find will be squared, and I can finish factoring it. So this problem doesn't give me a starting place. When it doesn't give me a starting place, I use my rational zero theorem. To create my list of possibilities, P over Q. Remember that they're going to be plus minus, where P comes from my constant and Q comes from my leading coefficient. Well, this gets to be a really small list. My factors of 2 are just 1 and 2, and Q is 1. So I only have those two whole number positive values and two whole number negative values. So no matter what I start with, at worst, I am only going to try 4 different numbers. So let's see if we can find a root, find a value that gives us a factor of our cubed function. Let's just start with our positive numbers. Let's start with 1. So if I divide by 1, I don't need any placeholder zeros. I'm going to use my synthetic division to see if I can find a remainder of 0. Okay, synthetic division. We bring down that first number, multiply on the outside, add on the inside. That's not going to work. That gives me a remainder of -5. That's not a root. It gives me a point on the graph, but that's not 0. That's not what I want it to be, so it doesn't work. Let's try 2. We're looking for that remainder of 0. That's what we want. Let's see if we get it. Bring down 1. 2 times 1 is 2. Add on the inside. 2 times 3 is 6. Add on the inside. Oh, look at that. That worked. We got a remainder of 0. So that tells me that that is a root or a 0. So my factor X equals 2 is a root, so my factor is going to be x minus 2. X minus 2 is a factor, and then I take that quotient, 1 degree less, so x cubed, this is x squared plus 3x plus 1. Okay, you know what? That's not factorable, which means that I found a root from my list of possibilities p over q. The other two are either going to be irrational or imaginary. Let's figure out what they are going to be. As me working out the factors, I've got to work with that. It won't factor. So I say, all right, quadratic formula, it's squared and it won't factor, so let's use our quadratic formula. You should have it written down there on your paper, or have it memorized. Negative b plus or minus square root b squared minus 4 times a times c all over 2a. Start to simplify that. We've got negative 3 plus or minus square root of 9 minus 4 is 5 over 2, and there is nothing else I can do with this. These are going to be, they're real, not imaginary, but they are irrational, which means they don't show up in our list of possibilities p over q. So I've got 3 roots, which is what I expected because it was a third degree polynomial. My 3 roots are 2, there's my real root, negative 3 plus square root 5 over 2, and negative 3 minus square root 5 over 2. Those are my irrational roots. But those are the 3 roots for that polynomial function. Alright, this one works a little bit differently. We are going to go backwards, finding the polynomial function. So instead of starting with the function and finding the roots, we are going to start with a root and we're going to find the function. Now this root we're given, x equals negative 4i, that's an imaginary number. Our conjugate pairs theorem applies here. Conjugate pairs theorem tells us that imaginary roots come in conjugate pairs. So if I have negative 4i for a root, I have positive 4i for another root. So it also pairs with x equals positive 4i. Now those are roots. Let's turn those roots into expressions, or factors. So if I move that over, I have x plus 4i, and I move that over, I have x minus 4i. And we're finding a function, so let's name our function g of x, polynomial function. Alright, these are conjugate pairs. I need to FOIL these together. I need to multiply them together. Multiply together. So g of x, my function, x times x is x squared. The great thing about conjugate pairs, the outside and inside products add to 0. Negative 4ix, positive 4ix adds to 0. And then last product, plus times a minus, is a negative 16i square. Now this I square we need to talk about. We got to do something about that I square. I know that the square root of negative 1 is equal to I, but this is I squared. So what if I square both sides of that equation? Then I have I squared is equal to, square root and square cancel out, I square is equal to negative 1. So that is a definition you need to remember. I is the square root of -1. I squared is -1. So anywhere I have an I square in my problem, I'm going to replace that with a -1. So g of x equals x squared minus 16 times a -1. Negative times a negative is a positive. And there's my polynomial function with the root that I was given. All right, let's look at another. This time I'm going to have a bigger polynomial function because I was given 1, 2, 3 roots. Are those the only 3 roots I have? Well, no, because if I have 2i, I also have -2i. So I know I have 4 roots. So we expect a 4th degree polynomial because number of roots is the same as the degree. So let's work our way backwards. We start with our roots. X equals 5, x equals 3, x equals 2i, and x equals -2i. We need to turn those roots into expressions that are our factors. Let's go ahead and name our function here. We did g of x last time. Let's do f of x equals. Well, if I move this over, it changes sign, right? So that gives me x minus 5, x minus 3, x minus 2i, and x plus 2i. So now I need to multiply all of those factors together. You always want to FOIL together the conjugate pairs. That's a thing. So every time, no matter what, make sure you FOIL together the conjugate pairs. We can start by FOILing these together as well. X times x is x squared. My outside product is -3x. My inside product is -5x. So that's -8x. -5 times -3 is +15. That goes in parentheses because I'm still multiplying. Now when I FOIL this conjugate pair, x times x is x squared. Remember we said that with conjugates our outside and inside products always add to 0. And then I have a -4i squared. But we know that that I squared is the same thing as -1. So I always substitute that in here. I never leave it as an I squared. So I've got x squared minus 8x plus 15 times x squared plus 4. Because a negative times a negative is a positive. So now I need to multiply this trinomial times a binomial. You can do this different ways. Any way that you successfully have done it in the past, had an instructor that showed you how to do it that way, whatever works. I tend to set up, when I have a trinomial times a binomial or anything larger, I will set up a grid. This is going to be a 2 by 3 grid. I'm multiplying x squared plus 4 times x squared minus 8x plus 15. And when I fill in those boxes, x squared and x squared is x fourth, x squared minus 8x is -8 cubed, x squared times 15. In my second row, 4x squared, 4 times -8 is -32x, 4 times 15 is 60. And you can see what your exponents are and where you need to combine like terms. So I've got x to the 4th minus 8x cubed. 4 and 15 is a 19x squared. I said 19 and I wrote it down wrong. 19x squared, and then minus 32x and plus 60. That's my polynomial function with those roots. All right, excellent, excellent. Now we are going to put these things together and we are going to do a few graphs. Let's see, we've still got 3 pages left. This is going to be another long video. Okay, let's do an example. In a graph, our polynomial function, first we have to factor it. If it's not in factored form, it's not in factored form, so we need to factor it. Factored, it is not, so we need to factor it. Y-intercept, that's easy. If I plug in 0 for x, y is -4. So let's go ahead and let's stick that on our graph. 1, 2, 3, 4. There's our y-intercept right there. Possible rational zeros. We're going to use our rational zero theorem. List of possibilities, p over q. P is 1, 2, 4. Those are the factors of p. Oh yay, q is 1. That makes life happy. So plus minus p over q values 1, 2, and 4. I need to factor it. It's cubed, so I'm going to need to find one factor, one root through synthetic division. I only have 6 values to try, positive and negative values. So let's try one. Let's try 1 and see how it goes. 1 goes into 1, 1, negative 4, negative 4. Let's see what happens. Bring that down, multiply on the outside, add on the inside. That's not going to work. That doesn't get me a remainder of 0. Let's try 2. And see what happens with 2. So 1, 1, negative 4, negative 4. 2, add, that's 3, that's 6, that's 2. Oh yay, look at that. That's a remainder of 0. That one worked. So my first factor then is x minus 2. Remember, this is my value for c. X equals 2, so my factor is x minus 2. And then I need to take my quotient and interpret that quotient. That is x squared plus 3x plus 2, and see if I can factor that. And it factors just like that. So then I've got x plus 1, x plus 2. It is fully factored now. Alright, my leading term comes from this, not in factored form, so x cubed, which means my end behavior is to start low, finish high. I have 3 factors that are going to give me 3 separate zeros. Each of those factors has multiplicity 1. 1 is odd, so it's going to cross the x-axis at each of those values. I put those values back, so I set it equal to 0. That gives me a positive 2, a negative 1, and a negative 2. So I've got intercepts at positive 2, negative 1, and negative 2. My behavior, my end behavior, tells me my starting place. I'm going to start low, hit all of those, and finish high. I was able to hit all my points, everything matched. My 0 multiplicity chart is right there to read. We got it factored and graphed. Okay, let's do the next page. Number 2, putting it all together. Third degree polynomial. So again, we're going to need to find one rational 0 through our synthetic division to get it down so that it's squared. It's not factored. Okay, that's a little different. Sorry, threw me for a minute. It's not factored, so that's my leading term, negative 2x cubed. In behavior, still odd, but now it's decreasing instead of increasing, so it's moving like that. My y-intercept, if I plug in 0 for x, 0, 0, 0, my y-intercept is at negative 6. Might as well go ahead and stick that on the graph. Now this is factored form. So I need to figure out my possible rational zeros and use them with synthetic division to find that first factor, and then I can use, I can factor the quadratic that's left. Alright, so there's p. Oh, we've got fractions, but that's okay. Hopefully we won't have to use them. So p is going to be 1, 2, 3, 6. Those are my factors of 6. Q, the factors of 2 are 1 and 2. My list of possible rational zeros, plus or minus, I've got positives and negatives. I've got all of that over 1, so I've got 1, 2, 3, 6, and then I've got to come back and put it all over 2. 1 over 2 is a half. 2 over 2 is just 1. That simplifies. I've already got it in my list, so I don't have to write it down again. 3 over 2 is 3 halves. 6 over 2 is 3, and it's already in my list, so I don't have to write it down again either. Okay, so there's my list of possible rational zeros. I've got 6 positive values and 6 negative values. Let's try and find something that will work. We can start wherever we want. I usually start with my positive values. So if I start with 1, I don't need a 0 placeholder. I've got -2, +3, 11, and -6, and I'm looking for a 0 there. If I start with 1, bring down that -2, multiply on the outside, add on the inside. Oh, I can tell right now this isn't going to work. 1 times 1 is 1, that's a 12. 12 added to -6 is not 0, so that one didn't work. Let's move on and try 2. So set up my coefficients. Remember that you can pause this video, try it on your own, and then see if I got the same thing you did. That may be a more efficient way for you to practice. -2 times 2 is -4. Add here, that's a -1. That gives me a -2. That's not going to work because that's 9, so that's not going to give me a 0. We can keep working through. I'm going to go ahead and tell you, you know what, no, let's keep working through. Let's try 3. If I try 3, we've got -2, 3, 11, -6. We're looking for a 0 there. Let's see if it happens this time. -2, multiply on the outside, add on the inside. That's a -9. That gives me 2. There it is. Look at that. -6 and 6 is 0. That checks. So that is a root, x equals 3, a 0, which gives me the factor x minus 3. And then I've got this quotient that I need to interpret and factor. So that's a -2x squared minus 3x plus 2. Oh, you know what? I don't factor quadratics with the negative first term. So I need to do one of two things. I need to either, let's just factor out the negative. That's a better way to do that because we don't want to divide it out yet. Let's factor out that negative. -2x squared. Factor out the negative. It changes all of those signs. So I'm going to write that negative down here, show it factored out. And then I've got 2x and x. If I put a 2 here plus 2 minus 1, that gives me 4x, and -1x. 4 minus 1 gives me that 3x. So there are my factors. So I factored out that negative. I used my 3 that I found with synthetic division, and then I factored it the rest of the way to get those 2 factors. Okay, so there's my factored form. Roots 3. This is going to be a positive 1/2, and that is going to be a -2. The multiplicity on each of those factors, the exponent would be 1, which is an odd number, and it's just going to cross. All right, let's graph those. So 1, 2, 3, 1/2, and -2. My end behavior is start high, finish low. So start high, cross, 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 hit all my points, and we get to finish low. Very good. Okay, excellent. Now we've got something without a graph. Find a polynomial function g of x with 3i and I as zeros. Ooh, and then we've got more stuff. So we're working backwards here. We've given 2 sets of information. Right here is our zeros. These are both imaginary, so that means automatically that we know we have their conjugate pairs. So we have 4 roots, so I'm going to have a 4th degree polynomial. That is enforced here. That's degree information, 4th degree polynomial. And then that is a check for my coefficients to see if they are right. This is something I do at the end. I'm going to plug in -1 and see if I get 60. So we added a little layer of information. We're going to start with this. Our 4th degree, we have 2 separate imaginary roots, so they will each have a conjugate pair. All right, function is g of x. I have 4 roots, which means I have 4 factors. They're imaginary, so they are conjugate pairs. When I FOIL those together, I'm going to get, for this first pair, x squared. Outside inside product adds to 0. That becomes minus 9i squared. And we know that I squared is negative 1. So that is x squared plus 9. This one, x squared, outside and inside products add to 0. Minus I squared, which is a negative 1. So that's x squared plus 1. And now I need to FOIL these two together. I'm getting lots of practice with FOIL. X squared times x squared is x to the 4th. This gives me 1x squared, and 9x squared is 10x squared. 9 times 1 is 9. So that's my proposed function right there. Let's see if it works. The next thing we're going to do before we decide, yep, this is my answer, we're going to use this check. We're going to plug in negative 1 and see if we get 60. So let's find g of negative 1 and see what it gets me. Negative 1 to the 4th plus 10 times negative 1 squared plus 9. Well, negative 1 to the 4th, that's just 1. Negative 1 squared is 1 times 10, so that's plus 10, and then plus 9. That sum is 20, not 60. Not 60. What would I have to multiply this by to get 60? Well, 20 times 3 equals 60, and that's what I want. So if I take my proposed function and I multiply everything times 3, all of my coefficients times 3, it's going to give me the function with the coefficients that I need. So I created a function, but it didn't get me a big enough value. When I plugged in negative 1, I didn't get 60, I just got 20. But 20 times 3 is 60. So now I can go through and I can multiply each term times 3. I can check it again if I want to, just to verify that if I plug in negative 1, I will get 60. But I'm telling you, we're good. Very good. Okay, let's look at number 4. Now, notice that this says it's a challenge. Number 4 is just, we've got that imaginary root right here, but it is in that a plus bi form where we have the real part as well as the imaginary part. So the conjugate of that root is going to be 1 plus I. And that just gets a little bit more complex with the process of how we do that multiplication. You are probably going to see this in my math lab, these steps. I don't want us to get bogged down in this until we have looked at Descartes' rule of sign. So I want us to look at Descartes' rule of sign, and then we will either come back, yeah, we're going to come back to that at the end of the video. All right, Descartes' rule of sign is our last theorem for this unit, this section. Variation of sign occurs when the sign of consecutive terms changes. So if I go from positive to negative, from one term to the next, consecutive terms. This Descartes' rule of sign is going to help us figure out, when we look at our list of possibilities, like right here, when we look at our list of possibilities, we've got 6 positive, 6 negative. What should I try first? Should I start with the positives like I tend to do, or should I start with the negatives? Well, Descartes helps us to figure that out. How do we know if we should start with positive P over Q or negative P over Q values? This helps us be a little bit more time efficient. So Descartes' rule of signs focuses on the idea of variation of sign. So if my consecutive terms go from positive to negative, so like right down here, let's just look at P of X. Positive to negative, that is a variation of sign. The next term is still negative, changes back to positive, that's a variation, changes back to negative. That's a variation. So there are 3 variations of sign for p of x. Okay? Now what this means for us is that the number of positive real roots is equal to the number of variations of sign in the function, or less that by an even number. So right here, I've got 3 variations of sign, which means that I have 3 or 1, less that by an even number means I subtract 2 as many times as I can. 3 or 1 positive real roots. That's what that tells us. Now, to check for negative real roots, I have to figure out first what is p of negative x. Okay? So let's come down here. Anywhere I have x, I have replaced it with negative x. Now this really doesn't take a lot of work. It's just what happens if my exponent's odd, what happens if my exponent's even. If my exponent is odd, I'm multiplying together an odd number of negatives. Negative, negative, pair up, negative, negative, pair up, and I've got a negative left over, so this term becomes a negative 3x to the 5th. The next term, I have an even exponent, 4. The negatives pair up, nothing changes. So this remains negative 7x to the 4th. You see? Here I have an odd exponent. It is going to change, so this becomes plus 8x cubed. Even exponent stays like it was, stays a negative x squared. Odd exponent, so that becomes a negative 3x. Constant is, that word constant means unchanging. Constant is constant. So I've created p of negative x, and I'm going to now check p of negative x for variations of sign. So negative term, that one goes, the next term's positive, there's a variation. There's a variation, I go negative again, negative term, negative term. So I have 2 variations of sign in p of negative x, which tells me that I can expect 2 or 0, because again, less that by an even number means I subtract 2 or 0 negative real roots. Okay, how does this help me? Well, when I've got a list of possibilities p over q, and I'm trying to decide, should I start with the positives? Should I start testing with the negatives? I might have 2 negative real roots. I might not have any. But I know I'm going to have at least 1 positive real root. So I look at those pieces of information and I say, you know what? We're going to try the positive values p over q first, because I expect that one of them is going to be a root that works for me. Now notice these are real roots. The number of predicted roots includes both rational and irrational, but my list of possibilities p over q only has rational numbers. It's using the rational zero theorem. So, for example, this function doesn't have real roots. It only has imaginary and irrational roots. So I can't solve it using what we have been working with. But generally, this gives us a, okay, I want to narrow things down. This looks like my better bet. I'm going to start here first. Okay, that's all the new stuff. I want us to jump back in, take a deep breath, get a drink of water if you need to. We're going to follow the pattern of multiplying this together to create our polynomial function. I've got a total of 3 roots, so I'm going to expect this function to be 3rd degree. All right, and here's how we want to set it up. And I want you to just kind of follow along with me here. This root 2 gives me the factor x minus 2. Then I've got x minus 1 plus I, and I have x minus 1 minus I. Those are my two imaginary roots, a plus bi form. They've got the real and the imaginary part, so they're more complex than what we've done so far. So this multiplication is going to get a little interesting. We're just going to kind of bring this x minus 2 down until we get to the end. We're going to be focusing here right now, okay? I want to think about distributing that negative. So now I have x minus 1 minus I, and I have x minus 1 plus I. I am going to group together my x minus 1s because they are the same in each. Now I'm going to FOIL this. So I've got x minus 1 times x minus 1 is x minus 1 squared. My outside product and my inside products still add to 0. A negative I times x minus 1 and a positive I times x minus 1 are going to add to 0. And my last product is a negative I squared. Well, what is I squared the same thing as? Remember, I squared is the same thing as negative 1. So that becomes x minus 1 squared plus 1. Now we need to FOIL this. So I think I can squish more in here. X minus 1 times x minus 1, and then I've got plus 1. All right. X times x is x squared. Negative x, that's a minus 2x. 1 negative times a negative is a positive 1 plus 1. Okay? Which gives me x squared minus 2x plus 2 as this. Now, remember I told you we were going to kind of let this sit there. We've let that sit there. X minus 2 all the way down. We haven't messed with it yet. Now we need to put that together. And so we would say, all right, f of x is equal to x minus 2 times x squared minus 2x plus 2. And do you remember how we did that 2 by 3? We did a grid, yeah? So let's go ahead and set up a 2 by 3 grid. We've got x minus 2, we've got x squared, negative 2x plus 2. So that gives me x cubed, negative 2x squared, 2x, negative 2x squared, positive 4x, and minus 4. So that my final function is x cubed, negative 2x and negative 2x is negative 4x squared, 4x and 2x is plus 6x minus 4. And it turned out to be a third degree polynomial just like we expected. But this was just a challenge because of those complex roots that have the real and the imaginary part. Knowing what to do here as far as grouping together and following your order of operations correctly. You're not going to have to deal with something like this on the test, but you will see it in my math lab, so I wanted you to have a good example of it in your notes.